Hello. Well, I've reached the point in the auger boring machine where it's time to build the adapter shaft. And the adapter shaft is used to transmit torque from the screw anchor motor to the augers, which are inside of the pipe that we're pushing through the dirt. And this is the front of the auger boring machine, and that shaft will pass through that hole in the center. Now, one of the issues with this is we're trying to join up two machines from two different areas of the construction industry, and the standards are different. Here we have the screw anchor motor, and this is used to drive screw piles into the ground. And in that industry, they use a square drive. And in this particular machine, they use a 5 1/4 inch square male shaft coming out of the motor. The auger boring industry uses a hex drive instead of a square. So, and this particular one is a 5-inch hex, 5 inches across the flats. And the augers themselves have a male hex on one end and a female on the other, but they're driven with the male pointing back towards the machine. So that meant I was gonna have to design and build a shaft that would be female-female, with a female square on one end and a female hex on the other. The final design is going to incorporate this, which we were able to buy off the auger manufacturer. But at the time, when we first started designing this, I didn't know if we'd be able to get a shaft like this. So I came up with an idea of how to build it. My plan was to get a series of plates, an inch thick, laser cut. Our local laser cutting outfit here can do very accurate work on up to 1 inch thick plates. So I was going to use 1 inch plates and just get cut out round on the outside with the correct sized hex on the inside. Then the idea was that I would just chamfer them on my lathe for a weld prep, and then just weld a series of plates together to whatever length I needed. Then I thought, well, I might as well just keep going, and I'll get a series of plates with a square laser cut out of them with the same outside diameter, and I'll just add as many of those plates as I need until I have the correct length of shaft. And I was pretty happy with that. It was going to be a lot of welding, but shaft was going to be a lot of work no matter which way a guy tried to build it. So I thought I would go ahead with that. And then I remembered something from my design days. I used to work for a company that designed oil field tools as a subcontractor for a company in Scotland. And one thing we always had to keep in mind is what the guys in Scotland referred to as the concast line in steel plates. And what that is when the steel plates are, when the steel to make the plate is originally cast in the steel mill, it's continuous cast mostly nowadays, and the piece that's cast solidifies from the outside in. So the last thing to solidify is the center of the piece of steel, the middle, sorry, of the piece of steel. And if there's any impurities in the steel that haven't floated to the top, if they're sort of trapped within that piece of steel, they tend to congregate right in the center of the plate, like I have this red line drawn here. There's also, from what I've read, there can be an alloy change as well. Anyways, the end result is that if you get a concast line in the plate, and it doesn't always happen, but it can make the plate weak and the plate can delaminate. So we were told when we were designing stuff, avoid situations like this, where you'd take a piece of plate, you know, say weld an eye on here, weld an eye on here, and then pull that way and that way, and put the center, the middle of the plate in tension. Because if there was a concast line in the plate, it could delaminate and pull apart and fail. So we always tried to design so that we never loaded plates that way. if we got into a situation where we had to load a plate that way, we didn't have any choice, what you can do is there are steel suppliers who can test plates to see if there is that defect in them. I think it might be done ultrasonically, but I'm not 100% sure of that. Anyways, there were situations where we just couldn't avoid doing, wasn't this specifically, but it was this type of loading, and we had to get those plates tested. I wasn't going to do that in this case, try and get plates tested. So I scrapped this idea. As kind of neat as I thought it was, I just was worried that if I got some bad plate, you could end up just, there's a lot of torque on this. It could potentially be 85,000 foot-pounds of torque. And if there was a defect in the middle of the plate, it would be pretty easy for this to just shear off. And I didn't want that to happen. So what we ended up doing is I ended up coming up with this idea for the square section. And this isn't really all that original. I've done this in the past to make adapters for this screw anchor motor. The only thing I did that was a little bit different from what we did in the past was I notched these pieces out in the milling machine so that we could just clamp it together and it would space everything correctly. And so you do that, and then these black curves here are just weld, and you just fill this full of weld. And we've done that before, and I didn't do any calculations or anything on the shaft. I just kind of made it the same way we made the adapters. They've been going for about 7 or 8 years with no problems. Pretty confident that this will work. Only reason I can go with this design is because we were able to get the hex shaft that I showed earlier. So as I showed you earlier, this is the hex shaft. We were able to get it from the supplier of the augers that we're going to buy for this machine. And what they do is they have a lot of these. They'll have a female and they'll have a male, and essentially the outside will be the same. And then when they make their augers, they use a piece of drawn over mandrel tubing as the core of the auger, and they weld the flights to it. So they just slide the DOM over here, it's chamfered back, and then they just fill this with weld. So we're gonna do something similar. We're gonna attach this to my square shaft, which is just made out of 4 plates. And this is it here. And we've just started the welding today, near the end of the day, so we'll pick up again tomorrow. But we had it clamped with all these C-clamps, and I took some measurements, and it all checked out, and it's square enough for what we need to do. So the welder tacked it up, and he's laid in 2 beads so far, but he's got quite a bit of filling to do. But anyways, you just fill all 4 corners. Then what I'll do, and I still haven't decided yet whether I'm going to put this in my lathe or on my horizontal mill, but I need to bore a hole probably about 3/4 of an inch deep and chamfer the plates back, and then this hex shaft will sort of go in like that, and I'll bore the hole so it's just a close fit on this surface, and it'll slide in. I'll face the bottom so that it sits square on here, so that we know that this is going to be, you know, you don't want this shaft like this and this shaft like this. You want them to straight, their axes to be straight. So I'll do that by bottoming this surface out on a shoulder that's machined square to the axis of this square shaft, and then we'll just weld that on, and that'll be the shaft. This end will fit over the screw anchor motor. I have to, after this is all done, I'll drill a hole for the pin that goes through to hold it on the shaft. And then this end is the 5-inch hex, and it's already got the hole in it for the same idea for the pin through. And that shaft, will stick out of that hole. So it'll come out pretty much to the face of this round piece, which is called the mud box. And then on there, I have to attach a couple of paddles, because what happens is the mud comes out of the pipe, falls into this, what's known as the mud box, and then the paddle comes along and dumps it out the chute. This is actually one of the plates here for the paddle. I got to mount it on some square tubes, and there's some other things. I can maybe make a video about making that as well. And it will bolt onto the square part of the shaft where it'll get a good positive drive. So anyways, that's the plan. We've got a bit of welding done, and I'll show some of the machining and some of the welding as we finish this shaft up. Well, the pre-machine before weld on the square part of the shaft is finished, or so I thought it was. You can see the fit here. Push that in. So we have a groove to put the weld in, and I was gonna chamfer the square part of the shaft back to give more room for the welding. As the welder pointed out, if we just didn't have the shaft so far in, he would have more room to be able to burn down right to the bottom of the groove. So what I'm going to do, fortunately I made the shaft longer than I need it, with the plan being that at the very last sort of moment I would cut it down to length and drill the hole in it, the cross hole, which also determines its length. I have extra, so what I'm going to do is I'm just going to face this surface back to reduce the depth back to the shoulder. We'll take it down, and then we'll have this stick out more, and then he'll be able to get in there and penetrate right to the bottom of the groove. This is the welding prep now after facing off the front of the square shaft. You can see we got some more room there at the bottom, and should be able to get a weld right down to the root there, and get a good full penetration weld all the way around. I just wanted to make a comment about the boring and facing head I'm using. It's a Adaptor UPA 4. This is the first time I've used it. I just got it 3 or 4 months ago. I bought it for my horizontal boring mill. It's on a 40 taper. But I don't have my horizontal boring mill running yet, otherwise I'd be doing this job on it. And so I've got it in my horizontal mill. I have a Narex 1 1/8, I think is the model, which is 1 or 2 sizes smaller than this one. And it's a nice facing head as well. It's on an R8 shank. I use it in my Bridgeport clone. But this is the first time I've ever had a Wallhopter, and they definitely seem to be a cut above. They're so smooth, and everything uses the same size hex. All the adjustments. And they give you this hex T-wrench, which doesn't seem like much, but it makes setting this boring head about 3 times as fast as the Narex. And since a lot of time is spent setting the boring head up, that's a big help. I'm really looking forward to using this on my horizontal boring mill when I get it up and running. And the nice thing is I can do all that work with 1/4 inch high-speed steel bits, and they seem to cut really well, and I seem to be able to take fairly heavy passes with it, so very happy with it, as I'm sure anyone who has one is. Here we have the final fit up of the 2 pieces of the shaft before we weld them together. We just put the hex shaft in the square shaft, put a threaded rod through it, and clamped it all together with a couple of bars. And aligned this hole so that it's square to the shaft, to the square part of the shaft, rather. And then the welder just scabbed together a bit of a fixture. That'll just allow him to rotate it into position as he's welding around. This shaft's starting to get pretty heavy. I think it's well over 200 pounds. And having square sides, it gets hard to roll that around on top of the welding table. So this should work pretty good. We know that this is mild steel because we ordered the material for it. This we're not sure. It could be a 41 or 4300 series alloy. So we're gonna treat it as though it is, and we're gonna preheat the entire shaft before welding, and then wrap it in insulation and let it slow cool. And hopefully we won't have any trouble with cracking or anything like that. So this is 21 hours since we finished welding, and we wrapped it in insulation. You'll see what it was at about 500 degrees when we wrapped it. It's still 170 degrees Fahrenheit in 21 hours. So the insulation has been pretty effective at cooling that down slowly. Hopefully that bodes well for lack of cracking in use. Well, after letting it cool for 48 hours, at which point it was at room temperature, we unwrapped the shaft, and this is the result. And I'm pretty happy with how it turned out. I think it's going to be fine. Not knowing exactly what the material is, we assumed the worst, and that it was a 41 or 4300 series steel. And from what I was able to determine, you're supposed to preheat and keep an interpass temperature of between 400 and 600 Fahrenheit, and we were always around 500 the whole time, and then a slow cool at the end, which we definitely had. So I think it's going to be okay. There's no obvious signs of cracking. But you know, the truth will come when it gets put into service and it sees its first heavy loads. About the only thing left to do to this shaft is we'll cut it to length and drill the cross hole. But that won't happen until we do the final fit up on the boring machine and we know the precise length we need. Yeah, the shaft, all in all, the shaft I think went pretty well. It was quite a bit of work, despite the fact we only have 5 weld beads on this, or weld locations, I guess, on this shaft. There was about 6.5 hours of continuous welding. The guy that did all the welding is my father-in-law. He's going to turn 75 in a couple of months, so he did a pretty good job. It's almost to the point where when someone asks me what is the shaft made out of, I could legitimately say a substantial portion of it is made out of flux core MIG wire. Anyways, the next time I show this, it'll be installed in the machine with the paddles on it, and that might give you guys a better idea of its final function. Anyways, thanks for watching, and we'll see you in the next video.